Alright, chemistry students, here we go on the final lesson of Unit 10, where we take a look at Dalton's law of partial pressures. So we want you to be able to state Dalton's law and then apply Dalton's law of partial pressures to describe the composition of a mixture of gases. So a lot of times, whether we want it or not, we end up with mixtures of gases. So we need to understand that each gas in the mixture contributes something to the pressure. And if we're looking at just the pressure of a specific gas in the mixture, then we can use the law of partial pressures to remove the pressures or figure out what the pressure contribution is of the gases that we don't really care about. And so let's get started with this and you'll see what we made.
Alright, so Dalton's law of partial pressures. It's for any mixture of gases in a container, the total pressure of the gas is equal to the sum of the pressures each gas would exert on its own. So Mr. Ferguson, if you'd be so kind as to walk us through this.
So we have three different containers. Each has a volume of 1 liter. Container A I wrote in red, and the calculations in red. B's blue, C's black. But in container A we have a half a mole of hydrogen gas. Container B we have 0.3 moles of nitrogen, and in container C we have 0.2 moles of O2, which adds up to a total of 1 mole of gas. So let's say that all three of those gases were going to be put into one box that had a volume of 1 liter, and we want to know what the final pressure is going to be. Well, according to this law, if we just find the pressure that each gas exerts on its own, that should equal the total pressure of the gas. So I just picked 273 standard temperature as the condition, and I used the ideal gas law, solved for pressure, and I came over and I worked it out for hydrogen here. And I got lazy because I was cramped on space. I did not put units in, so don't do as I do. Do as I say, always put the units in. But for hydrogen, what we've got is a half a mole of hydrogen would give us a pressure of 11.2 atmospheres. Taking our 0.3 moles of nitrogen, coming over here in the same ideal gas law equation, we get 6.7 atmospheres. Doing the same thing for the 0.2 moles of O2, we get 4.5 atmospheres, which when we add it up gives us 22.4 atmospheres of pressure. So now let's take the total amount of gas particles, 1 mole, substitute that into P equals nRT divided by V. That's this calculation. And when you take 1 mole times the ideal gas constant times the temperature divided by the volume of 1 liter, lo and behold, you get the same pressure, 22.4 atmospheres. So it works. And I think that was, when you have a mixture of gases, this kind of lets you figure out what the contribution of each gas is to the overall total pressure. And that's the use of this law. It's one of the uses. So let's take a look at an example problem on the next page.
So what this showed us in the last slide is that the pressure of a gas exerts is determined by the number of particles in the gas and not by the type of the particle in the gas. And this goes back to the kinetic molecular theory with ideal gases. All these gases are considered to be massless points in space, and they have
volumeless points. They have
that's
mass,
right.
But
volumeless points in space, and have no attraction for each other. So that pretty much takes away any type of consideration of what the molecule is, and leads it completely up to just being like little bouncy balls, which this does actually support. So the sample problem we're going to look at is problem 2 in our packet on page 50.
So if I was you, you could go right to page 50 and kind of work this out in the space there.
Yes.
And that because we're going to be assigning the rest of those problems to you, so you'd have kind of an example to go from.
So we have 2 flasks that are connected by a valve. Flask 1 has a volume of 5 liters and it contains a nitrogen at pressure of 0.75 atmospheres. Flask 2 is a volume of 8 liters and it contains oxygen at a pressure of 1.25 atmospheres. When the valve opens, the gases will mix, so we need to predict the final pressure. So like the last time, we're going to choose what type of gas law we can use. Last time we were given a volume, temperature, and number of moles, so we could find the pressures. This time we're only given a pressure and a volume. So this means we'd have to use Boyle's law. So if we solve each individual side,
So let's look at nitrogen as one thing.
So we would have to solve the Boyle's law equation. We have the initial set of nitrogen, which is 5 liters and 0.75.
So this is our V1 and P1.
And then we have the second set of conditions. We have to solve for the new pressure, but we know what the total volume is because we're adding the 5 and the 8 together to get V2. So we'd have 13 for our second volume. So let's plug this into Boyle's law.
So the pressure of just the nitrogen is going to be equal to P1 V1 divided by V2.
Which when you plug the numbers in, turns out to be 5 liters times
Yes, we have 5 liters times
0.75 atmospheres.
0.75.
And then divided by both of the volumes combined, which would be 13.
Liters.
And we get an answer of 0.288. And then you do the same for oxygen.
And I know what you might be wondering. Well, why did you make it one significant figure? Like I went 3 there. Well, this is an intermediate answer, so
Yes.
I don't want to over round that. I usually go at least a couple of digits beyond where I'm
Until
going to
the
be
end.
rounding it to 1 at the end. But for right now, I'm going to not call it 0.3. I'm going to call it 0.288.
Okay.
We'll do the rounding at the end.
So the next view for the oxygen, we're just going to kind of skip right ahead and set up in the numbers, I believe, would be fastest and easiest
Same
in this
equation.
case. Same
Yep.
equation as before. So it's going to be 8 liters
Because that's the initial volume of the oxygen.
times 1.25 atmospheres, which is its initial,
pressure.
divided by the total volume again.
Still 13 liters.
And you hit equals on that, and it's 0.769.
769 atmospheres.
So now we just have to add these together.
So summing them up should be the pressure of the mixed gas.
Yep. So what we have is 1.057 atmospheres, which of course, using correct sig figs, would be simply 1 atmosphere. So again, these laws require you to decide which gas law you're going to have to use. We can use any of the gas laws potentially.
Anyone that
Has pressure.
we can get pressure right out
So-
of. So that's we're going to pick out another example problem and show you in one more, I think, on the next slide. So one of the ways that partial pressure gets used is a lot of times we collect gases in the lab over water, like we did with the butane lighter lab. So you bubble the gas up through water and collect it in some kind of graduated cylinder or tube. Unfortunately, water ends up becoming part of the gas mixture then because water evaporates even at lower temperatures. So we use the partial pressure idea to kind of account and subtract out the contribution of water to the pressure. So here's a sample problem. We've got 82.5 milliliters of methane that we collected over water. The atmospheric pressure was measured at 755 millimeters of mercury. So that's the pressure of the gas inside the collection tube. And the temperature that day was 28 degrees Celsius. So we're supposed to find out the pressure of the dry methane. So Mr. Hunter, why don't you walk us through how to do one of these?
Well, this is surprisingly an easy problem. It's much like the one we did on that we said the butane lighter. The main thing we have to look at first is the temperature at which the water is at. And if it's a 28 degrees day, we're just going to assume the water is also 28 degrees. And up here in this chart we provided, you see the 28 degrees Celsius, and next to that, it's 28.3 torr. That's telling you that there is 28.3 torr of pressure of water in whatever sample that you're dealing with. So of that total pressure for the day, inside of that udiometer that we used, you would have to take the atmospheric pressure and subtract from that the pressure of the water to figure out the methane's partial pressure. So what Mr. Ferguson just wrote here was the atmospheric pressure equals the sum of the two gases that we currently have, methane and water. We know the total atmospheric pressure to be 755 millimeters of mercury. And we know the water's pressure to be 28.3. So we can easily subtract these away from each other, and you'll find that the final answer is just an easy problem, and it comes out to be 726.7 with using proper addition and subtraction rules, which would be 727, because the least known,
precise
is
place
the
value.
ones place. So that would be the mass, or not the mass, that would be the pressure of methane inside of that. So this is a really easy gas law problem, but they come in all shapes and sizes and difficulty levels. So just be wary of them. We'll try to help you the best we can with these. So have a good night.
Alright, so we're going to try a post-video question, and it's in 2 parts, so at least I think you can try the first part, and if you're having trouble beyond that, then we'll see, and we'll work on it in class. So we've got a reaction that's yielding carbon dioxide, and it's bubbled through the aqueous reaction mixture, which means it's going to pick up some water along the way, so you're going to have a mixture of water vapor and carbon dioxide. There's your volume of gas. Here's the temperature. So since it's a eudiometer, which is kind of an upside down tube in water, what we're going to know for sure is that the pressure inside the tube is going to be equal to the atmospheric pressure. Here's the atmospheric pressure. And so here's the 2 questions. First, determine the partial pressure of carbon dioxide. Then, the number of moles of carbon dioxide in the container. I've supplied you with a chart that's going to tell you the pressure, the partial pressure of water at various temperatures. So you can use that to get your partial pressure of water, and then see if you can calculate the partial pressure of carbon dioxide, and try to give the second one a shot as well. Give it a try. We'll talk about it next time.